Sometimes I forget things just as soon as I say them, but believe it or not, your computer can do the same thing. Why is it happening? Find out more next.
You're watching IT Pro TV.
Did you know that your computer can have short-term memory loss? Did you know that I can have short-term memory loss? Well, the reason for that is something that we call random access memory. And why does that actually happen? Well, this is the man that actually can let you know that, and that's Mr. Wes Bryan. Wes, this is kind of one of those subjects where everybody says, I know that I need RAM, but they may not know exactly what that means and what we actually have to know about it. So how are we going to tackle this?
So we're going to couple this with a little bit of show and tell. We're going to talk about what random access memory is for us, why it's so important, how we utilize it, as well as we're going to talk about, a little bit about specifications surrounding random access memory, because there are some industry standards, of course, big surprise there, right? And then we're going to look a little bit at where do we actually find that within our system units.
All right, it sounds like a lot for us to discuss, so head on over to the bench.
All right, everyone, come on over here and join me. And this is one of those episodes that really does deal with specifications. You know, just like any other technology that we look at, everyone out there, you have to kind of learn the language. You have to learn the jargon so that you understand. If we were to say, hey, I need you to get that DDR4 module out and install it in that DIMM socket or DIMM slot on the motherboard, would you know and be able to identify that scenario and come up with the right answer? So what we're going to do, and what I thought would be nice, is just to have a general discussion around RAM, not a lot of diagrams, if you will, and let's just start there. When we talk about RAM, what is RAM? You've kind of heard Ronnie alluding a little bit to it, but it's called random access memory. And random access memory is a type of memory that we've been using for our main system memory for a very, very long time. And these components don't really look like much. They're just little modules, if you will, on look like little chips, right, on a printed circuit board that gets inserted into a slot on the motherboard. And that's a lot of times that's all we see, right? But random access memory, right, it is what is known as a volatile storage mechanism, right? And what we mean is volatile, right? When we say volatile, what does that mean? Well, that means that we need to have an electrical current established and actually on that storage location to retain the information that's within it, right? That's what volatile means. Unlike maybe we say our hard drives, right, our solid state drives. These are non-volatile storage locations that we can use and store our information for reuse at a later time. Random access memory doesn't work that way. I want you to think of random access memory as more of this temporary workspace, right? I got a workbench here, right? And I'd like to throw things here up on the bench here and show you all, you wonderful viewers out there. And the bigger the bench, the more stuff I can put on it, the more stuff I can show you at one time. Well, believe it or not, your random access memory kind of works that same way, right? The more data that you want to actively be working with at one time, the more RAM, the more random access memory you're going to have within your systems.
And Wes, an analogy I like to use is kind of the little joke that I was making during our introduction here. It is equatable to the idea of short-term memory. RAM actually does help us in that way, where as long as I'm actually using it at that point, it's going to stay right there and available for me to use. It's just like when we're in the middle of a show, understanding what it is that we have to do. All the stuff that Wes is actually recalling, it's actually right there in his short-term memory. But as far as long-term memory goes, a lot of this has been built in over time, as Wes has taught this course over and over again over the years. And what ends up happening is that now gets stored in long-term memory as well. Things like a hard drive is kind of that same equivalent. So when we start talking about that idea of random access memory, he's letting us know the more memory that we have, the more things that we can do at one time, which is something I would love to actually say that I have more of. As I get older, I'm starting to realize I don't have as much as I think. So hopefully that analogy helps.
Most definitely, and thank you, Ronnie. You know, I think I'm suffering from a little bit of that myself as well. And one of the things I want to talk about real briefly is the best practice, right? When it comes to installing your memory, in fact, let's take a close-up view. I've got a motherboard here, and what we can see in that motherboard is that I actually have four what are known as DIMM sockets. We'll talk about what that acronym means here in a second, but I want to talk about best practices. It's best practice that if you're going to install RAM modules, that you install the same RAM, the same speeds, because it's important to understand that if I have 3 memory modules that are installed and I install a 4th memory module that's lower speed than these other 3, all 4 memory modules are going to operate at that lowest speed. So that's very important to make sure. It's one of the best practices when it comes to installing memory. Remember, if you install a lower speed module, that's going to cause all of the other modules to default and operate at the lowest common speed.
Now, Wes, you just showed us a motherboard right there that also has the slots as being different color.
Sure.
Could that indicate something for us?
It can, yes. And let's go back to what Ronnie was saying. Sometimes it can. We've got to be careful. Let's take a closer look here. Notice that we have a lighter gray here and we've got a black, right? This is what's known as a dual channel memory in our motherboard, right? So what does that actually mean for us? Well, what that means is that when we say dual channel, you have to recognize that a single RAM module in one of those slots has a 64-bit data path. It sits on what's known as the system bus, and that is the main communication pathway between the CPU and, well, main memory, right? And it's important to understand that each memory module has the ability to send 64 bits into the processor at one time. Now, if we have single channel architecture, then we're not really utilizing the true speed of our memory. See, our CPUs are so fast that they can calculate 3 billion calculations in a single second. There is nothing on our motherboard, not a single component on one of these motherboards is as fast as the CPU. So we use the random access memory because its access times are denoted in nanoseconds, right? Very, very fast, lightning fast storage. But we can increase the performance of this volatile storage mechanism by having multiple channels, each feeding in a separate 64 bits at a time. So I want you to think of it this way. All of your memory either does one of two things. It either talks to a memory controller hub, which controls access in between the CPU and the main memory, or even Intel sometimes today literally just puts their memory right on the system bus. So depending on the architecture, all right, imagine that highway, that one-lane highway, if you will, is 64 bits. And I can pipe in 64 bits as fast as this memory module and the CPU can work with it. Imagine if I took and put another highway right next to that one and we were piping in 64 bits on that highway. Now we have 2 data paths that are utilizing 64 bits, essentially doubling the bandwidth to a 128-bit data path. That would be dual channel versus single channel. And then you have triple channel, right? Now I think we're talking 192 bits, I believe is what that is, right? 64 times 3. Then you have also quad channel architecture. And that's like saying that we're going to have 4 separate data paths simultaneously pushing information in and out of the CPU. And that's what multi-channel architecture. And back to Ronnie's question, if we look back here, you can see that there is a color coordination sometimes. I got to be careful with the sometimes, right? It has become commonplace to color code these, so they let you know that the 2 gray ones here, the lighter gray ones here, if I install only 2 modules and I want to take care or I want to take use of those 2 64-bit data paths, then chances are I have to install 1 in the gray and 1 in the black here, right? Because they're both on their separate data paths. Now, that's not always the case, and I'll tell you why. You do have some just basic commodity type hardware like the one that we have here that sometimes they're all the same color, and what you need to pay attention to is the vendor specifications, because typically the RAM or the DIMM slots on the motherboard, which is what these slots are, we're going to talk about that in a second, we'll say DIMM 0, DIMM 1, DIMM 2, DIMM 3, DIMM 4, and then what they'll tell you is install, to take advantage of multi-channel architecture, install 2 modules, one in DIMM 0 and one in DIMM, let's say 2. And again, I'm just kind of making these up. Pay attention to your manufacturer. Now, what if you're going to populate the same memory type, same memory speeds across the entirety of all of the DIMM slots on the motherboard? Well, then you don't have to worry about it, right? You know you're populating them all, so you have them installed in what is called the right order, all right? So that's multi-channel architecture. You have single, you have triple, or single, dual, triple and even quadruple channel architectures today. And the quadruple channel architectures are what we see in things like Intel's i7 processors, and we'll talk about processors at another time. Now, I keep mentioning, Ronnie, it's one of those things that sometimes if you've been in the industry for a while, you kind of take it for granted. I keep mentioning the terms DIMM, right? Well, what do we mean by that? Well, the form factor, if you will, DIMM donates on our motherboard here the slot type, the form factor slot type. That's called a dual inline memory module. And in our desktops, our workstations, and our servers, these are what are known as DIMM modules, right? Dual inline memory modules. But that isn't the only one that we have. And if we take a bird's eye overhead view, you can see I also have another type of form factor here, right? And this is called SODIMM or SODIMM, depending on how you would like to say that. When we talk about SODIMM, what we're talking about is small outline dual inline memory modules. And if we look at these, we'll take a closer look at these, and let's look at these side by side, and we can see. Notice that the DIMM module is just roughly about half the size of the SODIMM is about half the size of the full-size DIMM module. The SODIMM modules are what we utilize inside of our laptops, what we utilize sometimes in printers as well. And by the way, printers can also use full-size DIMM slots as well. But the DIMM sockets are typically what we see inside of servers and workstations, desktop, just normal desktops, if you will. SODIMM or SODIMM, these are going to be what we see inside of our laptops. So that's a little bit about the form factors. Now, we also have to talk about specifications and standards. And again, ladies and gentlemen, I put a lot of this information inside of the show notes so that you can make some reference, some flashcards for your own reference, and I would encourage you to study these. There is a memory consortium that has overseen the standardization of memory for a very long time now. They're called JEDEC. And they have some standards that if you're first getting into the industry can seem a little confusing because they define two different standards. They define the RAM chips, and what I mean by that is quite literally the little black flash memory type chips that you see on here, and they also define the completed module. And these are two different naming conventions, all right? So you're going to hear something, and if you're looking at things like objectives, if you're doing some research and you're out there maybe going to spec out a computer, you're going to see terms like DDR2, DDR3, DDR4, and even today, potentially DDR5, even though at this time, the recording DDR5 is still kind of in draft and hasn't been completely finished. So what are we talking about? We're talking about the concept of double data rate. Now, I put in the notes a retro naming convention just for you. There's also one called SDR RAM. That's single data rate. That was something that they did after they came out with double data rate memory. They retro named the earlier one that was just single data rate. I'm not worried too much about speeds or anything like that when it comes to single data rate, but I will tell you, for a certification endeavor, it's going to be important to know, and let me just zoom in here real quick. See the pins that we have there, the copper conductors there?
The shiny parts.
Yeah, thank you very much, Ronnie, there. So those pin counts on a certification exam mean something. I will tell you, if you're speccing out a motherboard, match the RAM to what the motherboard says and you're doing good. However, between the different standards, you will find sometimes the pin counts are identical. However, what's not identical is that little notch right there. And that little notch, if we stay close up here, actually lines up with the notches that you see over here about halfway through the DIMM slot there, right? And that's one of the things that we also have to keep in mind, and that's why it's important for a certification endeavor that you know that some of them might have the same, some of the standards might have the same pin count, but they are not backwards compatible with each other because they are notched in different positions purposely to ensure that you don't install the wrong RAM. Now, why do we care about standards? Well, we care about standards because they define the electrical capabilities and the transfer rates of these DIMM modules. There is what is known as DDR. DDR, by today's standards, is considered legacy, and even DDR2 in all transparency. But again, If it's a certification endeavor you're going for, you have to prove that you know the jargon and the lingo and you can speak the language. So I want you to remember that SDR, single data rate, 168 pins. I want you to know that DDR is 184 pins for DIMM modules, but a little bit different for our SODIMM modules in the standards that we'd be putting in our notebooks and our laptops. That would have been 200 pins. You will also see some interesting designations for DDR. You might see something like PC 1600. What does that mean? Well, DDR actually is the standardization of the chip that is on the module itself. The completed module, JDEC also standardizes. So when you see PC dash and a number, that number that's at the end of it is the overall bandwidth that that module can produce. So when we say PC 1600, that means it can produce 1600 megabyte transfer speeds per second, right? So know that that's the difference between the DDR standard and the PC standard. And you'll start to associate these with what the DDR equivalent is. So for instance, if I took PC dash 1600 and I divided 1600 by 8, I would get what the DDR equivalent is. That would be DDR slash 200, right? It would be DDR dash 200. So I put some of the PC standards in here for DDR, double data rate RAM, if you will. But then they doubled the speed. And one of the things that a lot of these successive generations of DDR standards do are two things. They improve the bandwidth, but they also reduce the power consumption, the power requirements. They can do that at a much lower voltage. So with DDR, I want you to remember that the DIMM modules have 184 pins. The SODIMM modules have 200 pins. When we get into DDR2, it's double data rate 2. It doubles over the earlier speeds, and we have 240 pin DIMM modules with 200 pin SODIMM modules. Now remember what I said, everyone out there, that you might have some standards that have the same pin counts, but the notches are not the same, and that's true of DDR2 and DDR3, because DDR3, yes, doubles the data rate again, DDR3, double data rate 3, but it also reduces the voltage and it moves that notch. So we have 240 pins for DIMM modules, but the SODIMM modules are 204 pins. So there is a slight difference. One of the great things about the DDR3 implementation that I want you to be aware of is it increased the amount of RAM that you could have in a single DIMM module, 16 gigabyte DIMMs. So you could have a potential to have 8 DIMM sockets on a motherboard, and each one of those DIMM slots could potentially be housing a 16 gig module. And that is one of the great things about DDR3. Now, when DDR4 came out, which is what this motherboard is and what this motherboard is, DDR4, there wasn't really much of a speed increase. They kept the speeds around the same, but again, the voltages dropped a little bit more, and the per DIMM module, are you ready for this? 64 gigs in a single DIMM module. So if you had 8 modules on a motherboard, multiply it times 64. It's a massive amount of memory that we can get on a single system today. And the pin counts are up to 280 for your DIMM slots, and your SODIMM slots are going to be 260. And I also in the show notes have some of the module equivalents. So you'll see that DDR2 is PC2, DDR3 is PC3, DDR4 is PC4, and you'll see some of the equivalent module standards in the show notes as well. Now, it's interesting because objectives call out DDR5, Ronnie, but it is not completely finalized. It's not a standard. But I can give you a little bit for the exam so you'll be prepared, because one of the things I do know is that the pins stay the same. As far as the capabilities, we've yet to see that. It'll probably be another one where they're reducing the voltage requirements, and they're starting to do things like predictive data anticipation. Things like, well, in some of the earlier modules, they would use things like prefetch. Well, that technology is actually advancing. So there's ways that they can anticipate what's coming, and they can increase the bandwidth as well. A little bit more than what you need for this exam, but me, I love the technologies. I absolutely think they're great. So with that being said, Ronnie, what do you say we go ahead and kind of show them where the RAM modules will be located? And ladies, or just everybody out there, I just want you to know that we realize that there's a lot of specifications here. We've got them in the show notes. Please take the time to make some flashcards and get this information under your belt. So if we go to a bird's eye view here, I'm going to remove the case cover here to this PC. And what you're going to see here, if we can zoom in just a little bit, there, thank you very much. We've got two RAM module or DIMM slots in this motherboard here. And what you have are these two levers on the outsides of each one of these DIMM modules. You can see there's white and black here, but this one has a white lever here that I've already pressed down because I've got pretty big hands getting into this case, and one that's pressed down on this side too. And that allows me to remove this RAM module. And you can see what we have here is essentially we've got a DIMM slot or a DIMM module. This is a DD, and let me just double check. I'm telling you right here. Yes, this is PC4. And you know what? Let's go ahead. Let's go even closer. Let's see how really close we can get on this, Ronnie, because I'd like to see let them see that PC4 designation. You see that right there? That says PC4 3200, and then it's got some characters at the end. That's essentially an 8 gig DDR4 stick, right? And you can see that the chips are DDR4, but the module itself completed, we can see right there is PC4 3200. So that's some of the equivalents I wanted to show you. First of all, to show you where in our system case is the RAM even located, and then what are you talking about when you say DDR4 versus PC4? So you can kind of see how they stack up. Those are for a certification exam. Ronnie and I were talking about before we started. At the end of the day, once you've passed your certification, or if you're currently in a support role, you're going to be just look at the model of the motherboard, look at what it says it requires for RAM, and make sure when you purchase it and you implement it, you're implementing the same speed of RAM across the motherboard so that you get the full performance out of the RAM sticks that you're buying.
Yeah, when it comes down to it, that's pretty much what we're going to experience as just somebody supporting a regular desktop. But Wes, as an IT professional, though, there may be times where we actually go into different types of machines, such as servers, and we might find out something, even though the RAM looks the same, we might actually see that they're not the same, right?
That's very true. In fact, what Ronnie's talking about here is a really cool technology. I love technology. I hope you do too. And that's something known as ECC-based RAM. Let's go ahead and set the stage before we talk about what ECC RAM is and understand that they are two completely different types. And I like what Ronnie said, because going out the gate, you might look at it and they might look identical. So what is the difference, right? Non-ECC RAM is the RAM that we're looking at right here in our workstations, right? It's relatively inexpensive. I know money's always relative to, if you don't have money, everything's expensive, but relatively inexpensive. However, in our production level servers, right, our machines where our data is so crucial, we want some type of RAM that allows us to check the quality of the data, check the integrity of the information. And if that information has errors in it, apply some kind of algorithm or solution that can fix those errors. And that's where we have what's known as ECC RAM. So when we say ECC RAM, what do we mean? We mean error correcting code. See, ECC RAM is really good, and if you haven't seen a server boot up, it's kind of interesting on how it does it. It actually will, as it's going through its post and BIOS is kicking off, or UEFI is kicking off all the hardware and stabilizing it, the memory controller will send a little bit of data into a memory bank within that module. And then it'll try to read that information out and compare the two values and find out, are they matching? And if they're matching, then it knows that that's good quality error correcting code RAM and that we're all good and we can proceed with the boot process. So error correcting code RAM is typically a lot more expensive than your common desktop RAM, and they do not mix and match. You do not mix non-ECC, normal workstation RAM, with server ECC memory, because they are not compatible with each other, and that will cause your systems not to boot. So ECC RAM is something that I would also be aware of. Ronnie, there's one final thing just to throw a rock in the calm pond of understanding that I want to mention, and that's this concept of virtual RAM, all right? We have to really be careful, right? Because today's day and age, we talk about things like virtualization and virtual machines and supporting virtual machines with having virtual RAM. That's not the type of RAM that they're talking about in this context. What they're talking about is what we call virtual memory. I like that term a little bit better because it tells you a little bit more about what we're doing here. Virtual memory is this trick, I like to say. It's the wizard behind the sheet, if you will. And virtual RAM, at the end of the day, it allows us to provide a small portion of our hard drive or storage device. Could be a hard drive, could be a solid state drive. The mechanism isn't important, but the part of our internal storage media as a portion of RAM. Now, we still use this today. It's still built in our systems into what's known as a paging file, but it was very critical in the days when maybe you only had 512 megs of RAM, right? We don't think about it today because we have systems that have I'm sitting here with a very low-end system that I bought, and it has 32 gigs of RAM. So that's kind of archaic today, but you should know that our systems still use what's known as a page file, so that when the RAM starts to fill up and we have no more physically installed RAM to use, there's a piece of software called a virtual memory manager, and what it can do is it can say, all right, the physical RAM looks like it's full. I tell you what, we'll take this information that's not currently being used and we'll write it to the hard drive, and then we'll find that application that's looking for information in RAM and we'll write it into the RAM, and I'll swap that in and out, and the applications can continue to work. Microsoft recommends that you set your page file, that virtual memory location, at 1.5 times the size of the installed RAM. Now, that being said, today's day and age, if I have 96 gigs of RAM on a motherboard, I'm probably not going to allocate, what would that be, like about 100 and let's say 40 gigs-ish
somewhere around
to a page file. And that's a lot, right? So whether you use it or not today and actively set it to that 1.5 times the size of the physically installed RAM, you do have to know that your operating system is using a portion of your hard disk or your solid state disk as though it was physical RAM in something known as virtual memory, and it is being swapped in and out by a component within the operating system called the virtual memory manager. It allows systems that are limited on memory to allow them to continue to work even when the physical memory we start to hit its limitations. These are some of the things that I would know about your random access memory. Utilize your learner notes for specifications when you're sitting the certification exam. Those of you that are in support desk roles, match the RAM module to the motherboard, and at the end of the day, you're going to be doing well.
Thank you for watching IT Pro TV.
Storage technologies have changed over time. What do I mean by that? Find out more next.
You're watching IT Pro TV.
Hello, there are a lot of different storage technologies that you as an IT professional are going to encounter, and you have to actually be aware of some of the different things that go along with that. You might have to replace one or actually be able to evaluate one as well. And here's the guy that can help us to learn about both, Mr. Wes Bryan. All right, Wes, when it comes down to these things, there's so many different things out there that we have to consider. So how are we going to tackle this?
So what I thought we would do, Ronnie, here in this episode is we would identify the common storage technologies, and just like everything that we've been looking at when it comes to, different components, they do follow a level of standardization. So we're going to talk about some of the standardization and some of the things that you need to be aware of, whether you're sitting the exam and you're thrown into a scenario, or maybe you're thrown into a scenario in help desk, you can make the right choices.
All right, Wes, I see a PC kind of just about disassembled over there, so why don't we head on over?
All right, everyone, come on over here and join me. Yes, this is going to be more of that show and tell, because that's one of the things that we like to do. We like to get our hands on the technology, and this is going to be no exception to the rule. And Ronnie, I think one of the first things I want to talk about is a long-running storage technology that we've had really just since the earliest days of computing. And that is what is known as our traditional hard drives, right? Now, you might see the term hard drive might be abbreviated HDD. That's a hard disk drive. And the hard disk drives are ones that essentially is a magnetic media type. We write and read data magnetically, and it's what's known as fixed media. Now, if we could take an overhead view here, I've actually got one of these mechanical drives right here, and what we did, and don't worry, no drives were really damaged in the making of this video, we went ahead and I removed the torque screws that are in this drive. Now, I want to let you all know, please do not do this at home. And here's why. If you have a drive that you're going to throw away, okay. But you'll see right here, this drive, I had to actually remove some of the tape. And wouldn't you believe it, Ronnie, right across the top of that tape, it said, if this seal is broken, you void your warranty. So we want to be very careful with that. But you can see these are our traditional mechanical drives, right? This is what's known as a drive controller, right? In the early days, the drive controllers would actually be a big, huge expansion card that would be put into the motherboards. But when IDE came along, they came out with what was known as integrated drive electronics. And that just meant, hey, let's take the drive controller and let's integrate it into the actual drive itself. So the drive controller is actually what controls writing information and reading information. But let's go a little bit farther than this. Let's go ahead and let's take the top of this off. And we can kind of see here, and you can see my ugly mug here in the reflection of these platters right here. But what we have is we have a series of platters, and these platters, and I know I'm going to put some pretty bad fingerprints over here over these, but we have a series of platters that essentially spin. And we've got a series of read-write heads. Now, as these drives have increased in their density, which means that we can stuff more information in these, you can see that this is this is a 4 terabyte drive, and that's actually kind of small by today's standard, that we have multiple read-write heads. You can kind of see them, they're almost like a wafer. And what this does is this read-write head, it floats along these series of platters. And it looks for the data along the platters, or it will write or read, right? And then we have this actuator arm that kind of moves this magnetic read-write head back and forth. So that is your traditional drives, and it's important to understand that we have different speeds when it comes to the performance of these drives. And what we mean by speeds, Ronnie, is we're talking about the rotational speed of these drives. And they do vary. In laptops, you can see them as low as 5,400 RPMs. And it isn't common today to actually have them at 7,200 RPMs. But you have a variety of different RPMs that I would be aware of for a certification exam, and as well if you are going to make some recommendations. Average speeds, 5,400 RPMs for your laptop, 7,200 RPMs for your traditional workstations, if you will. Now, when you start talking about, for instance, in server grade, enterprise level grade, then we get into the 10,000 RPMs. And if you're talking about things like SCSI drives, which we'll mention a little bit here, I won't leave you hanging on that acronym, then you're talking about some that I've seen at 15,000 and even some experimental drives that are at 18,000 RPMs. And you have to understand that at that point, they are pushing the capabilities of rotational media within these devices. So that's a little bit about our hard disk drives, and I want you to be aware of how do we actually make connections. Older connections that sometimes still creep up on the exam from time to time. And yes, even in a support desk role where you have old point of sale systems, this is where I see them. You've got maybe a mom and pop store, they've got a point of sale system that they've had in place for a very long time, and guess what? They're going to be the ones that are swapping out the spare drives. If that's the case, then chances are they might be using an old technology called IDE, and that is the Integrated Drive Electronics. It was retro-named later on Parallel ATA, and we were using these ribbon cables to connect to our motherboards. However, today, that is really a legacy standard, and what we're using is now something known as serial ATA or SATA. Now, I have in the notes, I have some different SATA specifications that I want you to be aware of because it is important that you are aware of what SATA specification currently you are going to be using, and you can make a recommendation or a scenario on the exam, you can make the right choice. Serial ATA has 3 revisions. It has the first revision that would operate at 150 megabytes per second. Revision 2.0, we doubled that speed, 300 megabyte transfer speeds. And then the final specification for serial ATA is what is known as the serial ATA version 3, and that is a 600 megabyte transfer speed. There was a small, not widely adopted 3.2. I'm not worried about that too much because what we're going to see is that we got into newer technologies when we started needing faster speeds. The last one I'll say that's still common for mechanical drives, especially in your enterprise level networks where you have storage area networks, is something like the small computer systems interface, SCSI connections. And SCSI connections today are largely serial-based connections, and we've gone away from the earlier parallel communications due to things like interference and crosstalk. Sometimes today, when it comes to SCSI connections, you might not even see the old SCSI cables that we used to talk about, because a lot of times what they are is they have drive sleds that are embedded into the storage array that we slide these drives in and out. And that is one thing that I want to make you aware of if you've never heard this term. One of the great things about the serial ATA specification is it brought in this term known as hot swapping. Hot swapping is the ability to remove a failed drive, not if it's your operating system drive, let's just say that, but if you have a data drive that's failed, we can actually pull it out of a system while it's under power and replace it. And if we have certain technologies in place, we could potentially rebuild that information. So Ronnie, that's some of our traditional drives that we've had around for a very long time. They're a mechanical, magnetic media, fixed media, because we don't remove the platters. Once you open the drive, unfortunately, you can no longer use it. But we did that just so you all could see what does the drive look like on the inside.
Now, with that idea, a lot of people today, because of the way that the popular and not really commercial grade market has kind of moved away from these hard drives that are actually mechanical in their nature, people might think that they're a thing of the past. But in enterprises, we still see them actually being used, especially in long-term storage devices as well. One is because of the cost of them and because of how much data we can actually get fitted in there. But speaking of that, today though, we don't tend to see as far as like regular PCs go, where we're really putting in a lot of these drives. One, the machines get super heavy, but today the technology has advanced, and I think what we actually are going to be talking about here are what we call SSDs. Explain that a little bit more.
Sure, Ronnie. So SSD stands for solid state drive. Yes, it's an acronym. Yes, it's alphabet soup, and you need to be aware of what it is on the exam. I've got an example of a solid state drive right here, and if we take an overhead bird's eye view of this right here, what you're going to see is that it really doesn't look like much. It's very thin, right? It's very lightweight, and this is actually a form of what we call electrical storage versus the earlier magnetic media. And what this has is, it has these, if you can see here, these little NAND flash chips, right? They look like little memory chips, and that's inside of this drive. That's what's known as a solid state drive. Now, one of the great things about the solid state drives is they can actually have a very, very small, thin form factor, but they also do not read and write information to the storage mechanisms the way your traditional mechanical drives do. In this way, we're using it a lot like we are using system memory. Now, it is not system memory. Remember, this is a non-volatile storage mechanism that I can use to store data like any other hard disk drive and reuse it at a later time. But it has NAND flash chips on it, and it works a lot the same way that your memory in your system does likewise. So we have faster speeds than your traditional mechanical drives, because we don't have to worry about the rotational latency of the drive itself. How long does it take the ARM to seek out and find the information and return it back? we're basically using the NAND flash chips, much like a set of columns, if you will, in rows, and that's how we're writing the information and reading the information through electrical current. Now, one of the things that we have to worry about is drive the lifespan of these drives, because they write information a little bit differently. See, in a mechanical drive, if I want to write information to a portion of the disk, we can just overwrite any existing information. Solid state drives don't do that. What they actually have to do is they have to locate the area of the drive that they're going to write the information, and they pull out the good information and they kind of cache it, right, for use here after they perform an eraser process where they erase the cell, write the good data that was there back, and then the new data on top of that. So you've got a little bit more that's going on, and certainly a lot different than the traditional drives. So that's your solid state drive. Remember, in comparison to your mechanical drives, they're lower power, they require lower power, they have faster speeds because of the fact that they do not have to worry about rotational latency, and they're also they are shock proof, right? We don't have a lot of mechanical parts in there. So comparison there, solid state really is the way we're going today.
Now, you showed us two different types of solid-state drives there, right? One was that one that looked more like a rectangle, and then the other one actually looked like a chip there. Are those for two different specifications, or what are those about?
That's interesting. Okay, so what they did is, when it comes to form factors, if we take another bird's eye view, you'll see that these were the two primary form factors, right? We had what's known as 3.5-inch and 2.5-inch. And for the longest time, these were the form factors that we had for our drives. However, there is a newer technology that's been around for a little bit. I'm going to go ahead and get a really close-up view of this because it's kind of hard to see. This is what is known as a solid-state drive, but the form factor is what is known as an M2 form factor. All right, the M2 form factor you can actually see. In fact, let me go ahead and we'll zoom in. The M2 form factor we actually have on this board right here. You can see this little clip, Ronnie, this little connection point, and then you see a series of screws. And you can actually see that there are some designators on there. Notice there's a 2280, we see 2260, and Ronnie, I think that last one, if my old man eyes aren't too bad, it's 2242. All right, so what does that mean? Well, that actually determines what the dimensions of an M2 drive look like. We'll get to the connection points because that's a little bit different. That's a little different conversation. But I want you to know that the form factor of an M2, when you see something like 2280, that means that this little module is 22 millimeters wide and by 80 millimeters in length. And I believe this is a 2280 right here that I have. However, and if we could stay right there, you also have 2240s, 2242s, right? This is a very, very small little drive. All right, so that is a form factor. Now, we have to be careful and understand that what we're talking about with M2 is not the connection technology that we use to send information, but just the form factor of the drive, like saying the difference between a 3.5 and a 2.5. We're not talking about whether it's SCSI, IDE, or parallel ATA. So M2 is the same way. And I want you to be aware of that because we have two connection methods. The one that I'm showing you right here, believe it or not, is actually an earlier connection that's becoming largely obsolete today. And this is what's known as mSATA, right? This is micro SATA. And the big thing is, I want you to pay attention, Ronnie. Look at those notches there, right? So this is mSATA. And what that means is it's micro SATA, mini SATA, if you will. It is still using the serial ATA interface. It still has to conform to the serial ATA speeds, which means the maximum speed I'm going to get out of that drive is going to be 600 megabytes at best. And it's important to understand that the serial ATA specification was made for mechanical drives. It is not optimized for solid-state drives. So what they said is, hey, let's come out with a new connector and let's really utilize the full potential of speeds that we can see out of these solid-state drives, and that's through a technology called NVMe, non-volatile memory express. Now, you really can't see if we look in here real close. Doesn't look like much difference, but Notice the notch. Notice that notch right there. That's what can tell you the difference between what's known as an NVMe drive and what's known as an mSATA. mSATA still uses serial ATA. NVMe, though, on the other hand, is fascinating because it utilizes the PCI Express bus, and it can use up to 4 lanes of PCIe, which means there's plenty of bandwidth for these newer solid-state drives, and we can keep the performance levels up. So that's a little bit about your SSDs, as well as the form factors, and form factors also go over to your mechanical drives, but then your SSD connection or communication technologies, mSATA, and the more popular today, NVMe drive.
Now, along with these, of course, those are all internal components, but we still have storage devices that we can plug in almost like a peripheral, right?
Definitely, Ronnie, and it's interesting because these are kind of the precursor to what we think of modern solid-state drives, right? Let me kind of zoom in on this. We have what are known as flash drives, sometimes just generically called a thumb drive. And what it typically has is it has a USB connector, and on the inside you have potentially 1, maybe 2 NAND flash non-volatile memory chips. What's non-volatile, right? Remember that system memory is volatile in the fact that it's temporary workspace for your data, and if we don't have any power to it, we lose all that information. Not so with flash drives. Flash drives use the same type of technology, but it's non-volatile in the fact that I can write information to it. When I unplug it, that information is still going to be there when we need it. Finally, you also have things like memory cards, and there's a variety of standards out there. This is more of an older standard today. This is a full-size SD card, and you have a variety form factors. For instance, you have the micro and the mini SD cards, and these are commonly used in things like mobile devices today. Can be used in your PCs. In fact, sometimes your PCs will have card readers built right into them so that you can go from a mobile device right to your PC and you can utilize these devices. These are some of the technical specifications that I would be able to identify on an exam as well as in a support desk role when it comes to supporting your hard drives, your solid-state drives, and the communication technologies that they use.
Now, along with that, everything you've shown us really is kind of just saying, here's one drive, but I know that when we start moving towards businesses, we tend to see drives being able to be used together as well. So can you help us there too?
Yeah, Ronnie, we can do that. You know, that is what is known as the redundant array of independent or inexpensive disks, depending on how you look at the acronym. At the end of the day, it's what we call RAID, all right? And RAID arrays are a way that we can combine multiple drives together. We put what's known as a RAID controller card over them, and what the RAID controller does is it actually is kind of like I would say, like the master of ceremonies for both drive controllers that are connected, if you will, into this aggregation of more than one drive. Let me show you what I'm talking about here. We have some industry-wide standards when it comes to the redundant array of independent disks, and one of the most common ones that we have out there is what is known as RAID 0. Now, when we talk about RAID 0, the reason they call it RAID 0 is because, believe it or not, it offers a 0 level of redundancy. So what is redundancy? Redundancy just means that I have more than one component, that if one of those components, or when one of those components fail, the other one can take over and we still have access to our information. That's called providing fault tolerance to foreseeable component failures. Well, RAID level 0, or RAID 0 as they call it, isn't done for redundancy like the name would imply. It's actually done for performance increase, because what we can do is we can start we can have 2 disks here, right? It requires a minimum of 2 disks. And then you'll see that we have data 1 these are our writes, is what I'm trying to simulate. We have data to store, and how is it going to be written across these drives? Well, it's called striping because portions of your information that you have to write are written to 2 different drives within a set. So you can see that we have data, our first piece of information is written to disk 1, second piece of information is written to disk 2, and then likewise all the way down for our data set that needs to be stored. And you can see it kind of forms this stripe across 2 of these drives. Now, here's the thing to keep in mind with RAID level 0, because we have 2 drives, writing our information and reading our information. It's kind of like having a multitasker, and we get a performance increase. However, if one of these drives happens to fail, unfortunately, we no longer have access to our information, because it's not like saying, hey, I have half of my information left. The sets are two parts to a whole, which means if we lose one of the drives, we lose access to all of our information. So that is your RAID level 0. Now, Ronnie, one of the things that we need is a certain level of redundancy. And the redundancy comes in when we talk about RAID level 1. This is also known as mirroring. Now, we're also using 2 disks here as well. But what I want you to see is that the information is written to 2 different disks, and they're copies of the same information, right? So if we write something to disk 1 in a RAID 1 mirroring set, then that copy, that first write, is actually going to be copied, and we're going to have a duplicate write to the second drive. So this is why they call it mirroring. You have identical copies of your data, one for each drive. Now, this is called RAID level 1 because this is our first level of redundancy. And what happens is, if I happen to lose one of these drives, well, we still have a copy that is on that second drive within the mirror, right? So that is where we start to get fault tolerance. All right, now, let's talk about the difference between drive capacities or RAID capacities when we talk about the difference between mirrored and we talk about striping. When you talk about striping, if you have and we're going to use easy numbers for Wes's math. If you have 2 1 terabyte drives, then in a RAID 0 configuration, you get the totality of all 2 terabytes, right? Because you're just writing little pieces of information across the entire set. However, with RAID 1, if we talk about having 2 1 terabyte drives, remember, you're making an identical copy. So every time you write to one of the 1 terabyte drives, you're writing an identical copy to the second 1 terabyte drive. So figuring out capacities for a RAID level 1 array is to just cut the overall capacity in half. If I have 2 terabytes, 1 terabyte per drive, then I'm going to lose one of the terabytes in the overall capacity, because, again, we're writing twice. So I wanted to point that out too. But then there's another one out here as well, and that's RAID level 5. RAID level 5 is what's called distributed parity. It's striping with parity more simplistically, and it requires 3 drives. Now, when we talk about RAID level 5, we start adding additional information than the information that we need to write to the drive, and that's in the form of what's known as a parity information. So you can see we have 1 write to disk 1, we have a second write to disk 2, but then on the third disk we have a parity bit that's written. And that parity bit is distributed across all 3 drives. So what is the benefit of a RAID 5 array? Well, you get some of the benefits of the striping, but you also get a little bit of the fault tolerance. And that's because if one of these drives fails, let me do that a little bit different. If one of the drives fails, we have enough parity information that is stored on the other 2 drives within the set that we can continue to be operational. Now, you'll hear it say it's in an unhealthy state or the performance has been degraded, but you're still operational. And this is where the hot swapping side comes in. I can put in another, replace the failed drive, and believe it or not, with all of the parity information that's striped across all 3 drives originally, we can rebuild the information with the parity information that's left on those last 2 drives, and we're now fully functional again.
Now, with this, you mentioned that it has to have 3 disks, but we can have more than 3, right?
Yes, you can.
Okay.
Yes, you can. And Ronnie, the one good thing to keep in mind with a RAID 5 configuration is the fact that if you need to figure out what the total capacity is of your RAID 5 array, so let's say that we have a minimum of 3. We've got those 1 terabyte drives, 3 of them, right? You can consider an entire drive is the same amount of capacity of parity that would be distributed across all 3 of those drives. So you might think, well, like striping, right? We should have 3 terabytes. No, not really. You need to take one of those drives and reserve it in your mindset for the parity information that's going to be striped across all 3 drives. So you would actually have a 2 terabyte RAID array with these 3 different drives.
So, Wes, to make sure that, that we understand this, right? What we're saying is we can only afford to lose 1 drive in this type of array.
Yes.
So it doesn't matter whether we have 3 drives or whether we have 32 drives that are possible. We can only afford to lose 1 of those. If we lose 2 of them, Wes, what happens?
Too much parity information loss. Great point, Ronnie. And that's what brings us into the last one, where they wanted a way that we didn't have to configure or calculate parity information, but we wanted the ability to potentially lose 2 drives within a set. And the last one is what's known as RAID 10. And RAID 10 is a very expensive implementation because it requires at least 4 drives. And what you end up having is a combination. Sometimes you might hear the term nested RAID. That's all that this means. It means that we're combining the functionality of more than one RAID implementation. And in here, what we end up having is you can see that we have 2 RAID 1 sets. In this RAID 1, we have 2 mirrored sets. In this second RAID 1, we have 2 mirrored sets. But then in totality, across all 4 drives, this information is striped. So you might hear it also called stripe of mirrors. It requires 4 drives. It is one of the most expensive because of how many drives you need within this starting out. And then remember, anytime you mirror information, you're writing the same information twice, so that further reduces the overall capacity of this type of RAID array. But it seeks to get the benefit of a RAID 0 configuration and a RAID 1 configuration, and seeks to remove the parity calculation so that we can also keep performance levels up as well. One of the more expensive ones, but these are some of the specifications I would be aware of, so that when you sit that certification exam, regardless of the scenarios you are put in, you'll be able to come up with the right answer. If you're in a support desk role, you'll be able to make the right suggestions to the people that you're supporting.
Thank you for watching IT Pro TV.
Mysterious question here. What is it that actually connects all of our components together in the PC? Well, you'll actually find the answer out next.
You're watching IT Pro TV.
I just bought a new CPU. I also, of course, got a new hard drive and even RAM. But together, and just inside of a bag, it doesn't do anything. What do I actually need here? Well, Wes Bryan has the answer. So Wes, when we start talking about this is where people get confused, right? They start buying all these pieces of equipment, and then, I hate to say it, one of the hardest components for me to actually choose is what we're about to talk about. So what are we going to be taking a look at?
So in this episode, what we're going to be looking at is really the spine of the entire system unit, if you will, the backbone. It's what connects everything together and allows us to actually use that bag of hardware that Ronnie's talking about, and that's something known as motherboards. We're going to look at some industry-wide standards, so we're going to kind of show you around the playing field, if you will, of a motherboard and talk about some of the connections so that you, if you're sitting in an exam, will be able to get those questions right. And if you're having to support somebody and make recommendations, you'll also get those suggestions right as well.
All right, looks like you have several motherboards over on the bench. Why don't we head on over?
All right, everyone, come on over here and join me. Yeah, this is one of my favorite things, about this series is being able to really show you all, our wonderful viewers out there, a little bit more about the technology. See, motherboards are that necessary component, and what they do is they allow us to connect all the other system components together so that we can use them. You heard Ronnie alluding to it, things like our CPU, things like, for instance, our system memory. How do we gain access and use our hard drives, our solid state drives? Well, that is all through connections to one of these components, right? And I've got a variety of them here because we do have to talk about some different ones. Now, if we take a bird's eye view, you're going to see motherboards definitely come in multiple shapes and sizes. Now, some of these sizes, and if I get this one right here too, you can see I got a very super small motherboard up there likewise too. So motherboards, they actually follow what is known as industry-wide standards, and these industry-wide standards, what they will do is a lot of times they will dictate what is the shape of the motherboard and what are the arrangement of the components within that motherboard. And everyone out there, I have to tell you that standardization is a very good thing, because if we have standardization, then we know what we can expect when we talk about the size, the shape, and the dimensions of our motherboards. And I want you to be aware that if you are going to be endeavoring to support these devices, make recommendations on what type of motherboard you should get, there are 3 form factors, shapes, that must match in any PC build. That is going to be your case, because the case follows the same standardizations that our motherboards do. Your power supply has to follow the form factor, and that's based on the different standards and how we connect the main power sources to the motherboards. So we have our case, our power supply, and then at the end of the day, the motherboard. Because the motherboard actually sits on the side wall of the case. If you're looking at your desktop, maybe you got a workstation right now and it's standing upright, then what you'll see is that on one side of your case, you actually have the motherboard is bolted to the sidewall of your case. Now let's talk about some industry-wide standards, Ronnie, because we do have to mention some specifications. And ladies and gentlemen, I've filled up our learner resources, our notes, with a bunch of those specifications for you. These are going to be those things that unfortunately are just flashcards. But remember, if you need to prove that you can speak the lingo of this industry, then these specifications are going to be important for your certification endeavors as well as any recommendations that you might make. So let's talk about an oldie but goodie, and this is the one that's right here in the middle. If we look at this, this is what is known as an ATX standard. It's Advanced Technology Extended. Now, I will tell you that the one that is right next to this is what's known as a micro ATX. So as far as what the components are, the components follow the same specification, but it's just the dimensions that change a little bit. So let's talk about Advanced Technology Extended. This actually goes back to the days around 1995. Intel tried to give us the next greatest thing over earlier standardization, motherboard standardizations that we don't really have to worry about, that are beyond the scope of this discussion. And that was this ATX standard. And what it did is it defines a 12-inch by 9.6-inch dimension of the motherboard. Now, as time would progress, we would get other dimensions too. For micro ATX, you're going to see, and some different variations on the ATX standard. But largely speaking, when ATX came out, this is the standard that we would be following, and all of our PCs in the industry pretty much would be following. You will notice, and I'm going to go ahead and I'm going to get a really close-up view of this, because the one thing that it also defines is what the power connector is too. So when this first came out, this would have been what is known as a 20-pin main power source connector. However, throughout the years of the standardization, that connector wouldn't provide the power that we needed, for instance, for connectors like the PCI Express bus. So what you would see is that they would add additional connectors for CPUs. So you might see that you also have a 4-pin CPU connector, and that would have been called a 20 plus 4-pin connector. Today, what you see right here is largely what the standard has gone to, and that's a solid 24-pin main power connector. Yes, that is important, because remember, that is part of the form factors that you need to keep in mind when you're building a PC, because the ATX power supply has to match that connector. And that's one of the reasons, many reasons, that those form factors need to be in agreement with each other.
Now, Wes, you had previously mentioned that it's on the back side of that computer case. So is there a specific standard also then for computer cases?
There is. So, and I'm glad you asked that. So if I needed an ATX, standard ATX motherboard, then I need a standard ATX case. I also need a standard ATX power supply because, and I say standard because of the standardization here, and that's important. Now, the other thing that's really, really cool that the ATX brought into play, and it doesn't matter which one I grab. I love it. Even if I grab the micro ATX here, again, its dimensions are smaller, but it's what it offers is the same thing regardless of which ATX board you're talking about, and that's this back I/O panel. You'll see that this I/O panel has a standardized dimension. Now, let's be careful with that because it doesn't define what we need to put, what connectors are available within that range. But if I take another motherboard and I stack these basically together, you're going to see that the I/O panels almost are identical, right? And that's one of the things that the ATX standard brought in is this I/O panels. The I/Os are now integrated in the motherboard, where in earlier standards, if you wanted that functionality, typically it was going to be an expansion card that you would have to put on the motherboard to bring that into play. So that's another thing I want you to remember, that I/O panel standardization. The other thing that the ATX brought in too is one of these old ports that by today's standards you're saying, Wes, really? These are PS2 ports. For our gamers out there, this is not PlayStation 2. It's Personal System 2, if you will. And these are our mouse and our keyboard ports. Now, it really doesn't matter which one you connect up, but traditionally the green has been for your mouse and the purple, if I remember right, is going to be for your motherboard. They combined them today and they do the same thing on the micro ATX. So that PS2 port was something that the ATX standard brought in as well. Another great thing is the position of the CPU. If we look at an overhead view of these, you'll see that our CPU, if we put these in the case, it's going to align right under the power supply fan for increased cooling. One other thing that your ATX standard brought was a reversal, is the circulation. All right, we actually now pulling cool air in from the front of the case. As heat rises, it's exhausted out of the back of the case. So a lot of great things when we talk about the ATX standard. But it certainly isn't the only standard that I want you to be aware of for certification exam or support desk. There's another one out there, and that's called the ITX. The ITX board, believe it or not, everyone, it has all of the same features of ATX. It really isn't any different, with the exception. That was actually invented by a company called VIA Technologies, and the goal of an ITX board, and a variety of different size and specifications, is that it provides low power technology, all right, fanless. The cooling systems are passive cooling systems. We don't have things like CPU fans that are on top of heat sinks within these ITX boards. They can do very low power, they use low powered CPUs, and they can be passively cooled, very, very quiet. Now, these primarily are your two main standards that I really want you to be aware of. There is another one that they put within the exam, and that's what is known as BTX. BTX was not a widely adopted standard, and Intel tried to replace the ATX standard by coming out with balanced technology extended. Some of the things I want you to know about that is that it was intended to be the replacement for the ATX, but the ATX is a tried and true standard and has been around and is still more of the industry standard today. It had a better thermal design, which it opened up certain locations within the motherboard that would allow air to pass over this and cool it a lot better. It also did things and brought all the components. So if we take an overhead view here, it took the components and it put them closer together, and that was to try to reduce the operational latencies that we had on the motherboard. But again, BTX did not really take off. It really wasn't widely adopted, and today we have the ATX standard. So know your ATX, know the ITX standard, and know the BTX standards as well.
Now, with those motherboards, they will have, of course, depending on how much money I'm assuming that you'd spend on them, different connectors that we might choose to use. And that's why I said at the beginning, I find it probably one of the most confusing components to actually have to purchase. So what would we generally look for?
Sure. So you have, when we talk about our motherboards, if let's look at the micro ATX that I have right here. This is a really cool board because what we end up having on it is we have a variety of bus architecture for expansion slots. One of the great things about your motherboards is manufacturers can vary the price points on the motherboard based on the functionality that you need. And what you can do is you can extend the functionality by using things like these expansion slots. You have, for instance, right here is your PCIe slot. This is a 16-lane card that would be put in this. And then you have two different PCIe one-lane slots, which means that they're only using the single-lane throughput, right? So you can see the PCIe interface. Now, the older interface that we would have, I want to kind of bring this here too, and we'll kind of show this to you, is the peripheral component interconnect. PCIe or PCI Express has largely replaced the earlier PCI sockets today, but you will still find them on motherboards for backwards compatibility. So what we're talking about is peripheral component interconnect, an earlier parallel-based technology that was sharing the electrical bus with all the other devices that were in PCI. So it has a limitation on its performances. And then we moved into the PCIe. So you can see that this one has three of our 16-lane PCIe slots, and this one has two of the single PCIe slots. So those are some of the connectors as far as expansion cards go, but unfortunately we have a lot more we need to be aware of. We've kind of talked about the power connector already, so I've already established that. We've shown you that. Remember the power connectors based on the ATX standard, the 20, the 20 plus 4, and the 24 pin connector. We also have other connectors that we need to look at too. So you can see right here that we actually have what are known as serial ATA ports here likewise too. You could have something like an M2 port here. So you can see your M2 port, or excuse me, your M2 socket here, and you can see the different mounting points for 2280, 2260, and 2242. So the different lengths of the M2 slots. Those are important as well. You also have additional what they call headers, and these are USB. For instance, these are USB headers right here. But then if you've ever pushed the power on your computer and you've seen kind of like the activity lights, Ronnie, if you've seen the power light come on, right? Those are actually from a different set of headers that we typically connect via our case. And you can see that these are also down here in the mix. And what these are known as are our front panel headers. I've got another one here that I can show you that's actually kind of color-coded and doesn't just kind of blend in with the background. So these front panel headers, notice there's a color coding right here. All right, and what this is, these are all the case connections that allow you to push power, allow you to do a reset, your drive activity light indicator, all of those little connectors connect to this header. So those are the headers on the motherboard that I would definitely be aware of. There are a couple other things that I might just take the time here real quick to mention. I did mention the 4-pin CPU power connector. That was originally brought in for the Pentium 4, but today we have another standard, and it's an ATX standard as well as also known as an EPS standard for more server-grade enterprise, but it's been brought into the ATX standard, and that's that 8-pin power connector right there. That's an 8-pin CPU connector. So I do want you to be aware of that likewise too, because your multi-core processors that we're using today, they can't just use a single 4-pin P4 connector. They will use 2 of them together. Sometimes you'll see in compatibility power supplies that they have 2 that you can combine, or maybe they have a single 8-pin connector as well.
Yeah, when we come down to trying to think about what to choose, right, if we're building a computer, it really comes down to what it is that we want to do with it. A gamer might actually choose a different motherboard than the one that I would choose for something else. So it's important that we understand what the capabilities are and the different headers that we actually need, how much RAM it can hold, and what CPUs that will support, and even the idea of cooling systems too, right, Wes?
Most definitely. So when it comes to cooling systems, you know, we typically have a certain level of what are called heat sinks, and these heat sinks are installed on top of your CPUs, and we adhere our heat sinks with what's known as thermal compound. A heat sink really is nothing more than a block of metal. You can actually see some of these on the chipset of this motherboard right here. See this big block of metal? That's an example of a heat sink, and that will dissipate any excess heat, and this has actually got a heat exchange system. This is a gaming board like you were talking about, Ronnie, and you can see on the MOSFET too, our capacitors up here that do voltage regulation, they also have a heat sink likewise too. And then when we mount our CPU, we have a heat sink that sits on top of that. Now, before we put the heat sink on, we put a little bit of thermal paste, and what that does is when we put that heat sink, it bridges that metal on metal gap to allow us greater heat transfer into the CPU, or from the CPU into the heat sink, and then on top of that, we end up having a fan. So the CPU fans, you can see, for instance, there is a small little CPU fan header right here, and you can see just that little connection, and you can see CPU underscore their fan. That's going to be the fan that's going to connect, and it's going to ultimately cool our CPU. So know that your system fans and CPU fans, they might be connected to headers on the motherboard. If they're not connected to the headers on the motherboard, they are not going to be controlled by the mother's BIOS or firmware platform. So a couple of considerations that I would be aware of.
So what are some other motherboard compatibility issues we might want to think about?
Well, the great thing is, Ronnie, if we're using something like this, so if we take our bird's eye view again, if we're using something like this that are industry-defined standards, right? Like, for instance, these two right here, Micro ATX, your standard size ATX, then I know that if Ronnie says, hey Wes, I need an ATX board, I know right away that I should be able to find an ATX case and we should have some compatibility between the two, right? We're following an industry-wide standard. However, I'm going to slide these down a little bit. I want to show you that all motherboards are not treated equally. So for instance, I have a laptop motherboard right here. It has a lot of the same components that our main motherboards do, but this one doesn't follow a standardization, and that's very common for laptops and notebooks and mobile devices, that they do not follow any standard. So when we talk about compatibility, you do not have intercompatibility like you do with the standardized form factors. We also have things like mobile devices, right? And let's take a really close-up view. Doesn't look like much, but there's a motherboard, and that's a motherboard to a Samsung phone. And you can see all of the small components there too. Now, these type of motherboards are not compatible with one another because they do not follow an industry-wide standard. And last but not least, even though I don't have one here, I would say the same thing is going to be with when we talk about server-based motherboards. Server motherboards are typically going to be very proprietary, and they're specific to the servers that they're in. And whether there's compatibility, you have to check with a vendor. One of the last things that I need to mention about compatibility is Intel versus AMD. Your CPU sets a lot of the architecture for everything that we do inside of the computer, and believe it or not, that is no different than with the motherboard. So if I have an Intel motherboard, I need an Intel CPU. If I have an AMD motherboard, I need an AMD CPU to go with that motherboard. Intel and AMD do not cross-pollinate, and they are not compatible with one another. So that's one of the final things when it comes to compatibility that we want you to be aware of, so that if you're sitting your certification exam, you're going to be able to identify some of these concepts, get those questions right, and at the end of the day, if you're in a support desk role, you're going to be able to make the right recommendations to the end users that you support.
Thank you for watching IT Pro TV.
UEFI? BIOS? Is this a Wheel of Fortune game? We'll find out more next.
You're watching IT Pro TV.
Sometimes the acronyms, of course, continue to get more confusing, and we are actually here with Mr. Wes Bryant, who, though, can help us to dispel this idea. So, Wes, this is probably one of the more confusing things that people that are just entering into the support realm maybe don't have a good grasp on. So how are we going to tackle this?
You know, one of the things I thought we would do, Ronnie, the industry certainly hasn't helped us out when it comes to naming conventions. It certainly gets confusing. So, you know, these two technologies are firmware platforms. So what I figure we would do in this episode is we would tell you a little bit about what firmware is, why we would make one choice over, you know, BIOS maybe over UEFI or the other way around, and then we'd look at some of the settings that we're going to use, that we could potentially configure in our firmware platforms today.
That sounds like a great idea.
All right, Ronnie. Well, this time we're going to switch it up. Ronnie, I'm going to kick you over to the bench. So why don't you head on over to the bench for us this one? All right, ladies and gentlemen. So yeah, we're going to have, Ronnie is going to be driving for us, because what we have is we have a BIOS interface up here. And one of the first things I want to tackle is this little term right here. And you'll see it. They actually did not help us too much, because they combine both terms, UEFI and BIOS, all in the same namespace here. So what are we talking about? Well, let's go back in time here. When we talk about BIOS, we're talking about the basic input-output system. When we talk about UEFI, it's called the Unified Extensible Firmware Interface, and that's what I want to focus on, firmware first. What is firmware? Well, firmware, not quite software, not quite hardware, got kind of a funny name, sits in between. So what is it doing? It's actually a piece of code that when you push power on your computer, the firmware platform starts to find out if all of the components within the PC are available, and if they are not only present, but it starts to stabilize them and bring them online so that our operating systems, after the boot process is finished, can take over, and we now have access to our hardware through the operating systems. Now, BIOS, Basic Input Output System, this is one of the oldest ones. In fact, this goes back to really the 70s in 16-bit systems, and it's called Basic Input Output System. It was one of the first firmware platforms that we had, and it does have some limitations. If you're using legacy, as we call it today, BIOS, then you're going to be limited to 4 partitions on your drives and a 2 terabyte volume size. Well, if you think about it, that firmware platform was built in a day when we had 16-bit systems, right? So we weren't thinking ahead that we would need something more, that we would need something that would provide faster boot times, that would get us around those 4 partition limitations and 2 terabyte volume sizes. Well, UEFI comes in. The Unified Extensible Firmware Interface, actually, why you would implement that today is because you no longer have 2 terabyte limitations. In fact, UEFI BIOS can expand volume sizes out so large that they don't even make sense. We're talking 9 zettabytes.
A zettabyte? That sounds made up.
It does. It absolutely does. And it's mind-boggling how large that they've actually made the volume sizes, right? So we're talking about beyond a terabyte, beyond a petabyte, beyond an exabyte, right? Because 8 exabytes is about what traverses the entire worldwide internet in a single day, and we're talking about the measurement beyond that. So just mind-bogglingly large, right? And another thing is you don't have that 4 partition limitation. UEFI can actually support up to 128 partitions. With BIOS, it uses something known as a master boot record, an MBR, to bootstrap the operating system. And the problem with the MBR, that limitation that we're talking about, one of the other limitations is the fact that if the MBR gets corrupted, your systems will not boot. UEFI uses something known as a GUID partition table, a GPT, and it actually has redundant entries, so that if one of the entries gets corrupted, you can fail over to a protected entry and still bootstrap the operating system. Not to mention, when it comes to UEFI, you have faster boot times. And that's one of the great things. Now, with industry-wide standards here, right, it's nice, but they actually combine both terms here. You see UEFI BIOS. So I want you to know, from a certification exam point, UEFI and BIOS are distinctly different, but because so many people recognize the BIOS name, some manufacturers just combine the two. They are distinct, separate technologies. So those are some of the things to be aware of when it comes to your overall firmware platform. Now, there's other things that we can do too. So for instance, we can look at some of the configuration that we could do right here under config, and it's going to be specific to your platform, right? This is the BIOS in a Lenovo or a Lenovo ThinkPad. But you can see some of the things that we can do here. So for instance, we can configure our network adapter to do things like Pixie boot and boot from the network. We can do different configurations, power, CPU, for instance, Thunderbolt 3 you can see. So you can see that we can do some basic level configurations in here too. Another thing that's important in your firmware platform is making sure that your system date and time stays accurate, and that's typically held in a volatile memory region through something known as CMOS. Well, you can actually see your system date and time here, and you could set it. One telltale sign that your CMOS battery that holds and retains these settings is failing is if Ronnie was to come in here and he was to set that date and time, we reboot the system and it reverts to the original date and time that this firmware was actually pushed out, right? So inaccurate. It lets me know that there's probably a battery that needs to be replaced here. Now, other things that we can do is we can set boot options in here. We can say, hey, I want the default boot device to be the hard drive or the solid state drive, whichever, the local disk. We could set things like, for instance, we could say, hey, I want you to boot from the network adapter, or maybe I've got this USB thumb drive and I'm going to put an operating system on it, and I need you to boot to the USB thumb drive. Well, you could also set things like boot orders here as well, too. So you can see Ronnie's got the example of, for instance, a network Pixie boot that we could do here. And again, this isn't going to be specific to BIOS or UEFI. These are some basic things that you can set within your firmware platform. However, one of the things, many benefits that UEFI systems allow us to do is the ability to go beyond just basic firmware protection. So if we get into the security section, one of the things you're going to see here, this is not specific to UEFI. there's a password. That you might hear called a user password, you might hear it called an administrative password, you might even hear it called a boot password, or you might have a combination of the two. So the supervisory password, as it's called, allows you to not only boot the operating system, but do exactly what Ronnie's doing here, and Ronnie can get in here as a supervisor and make modifications to the firmware settings, right? If you just have a user setting, that means that they can just boot the system, right? So you might hear it called a boot password as well, too, just generically. So we can set things like that. But UEFI, one of the things that it adds, passwords, that's going to be BIOS UEFI support as well. However, if we can get back to some of those basic security settings, one of the things that we're going to see here that I'd like to mention is this secure boot down here. And this is a really cool feature of the Unified Extensible Firmware Interface platform. It works in combination with something known as a TPM, a Trusted Platform Module. And in order to have it, you have to have this cryptographic processor, if you will. It's a processor that stores security information in the motherboard of the system. And when you implement secure boot, what it's going to do is it's going to check what the current state of the drive is, and does it trust and understand the bootloader that's about to bootstrap this operating system. And if it does, it allows the system to boot up. However, if there's tampering or it's an untrusted bootloader, it will shut the system down and will not allow you to boot it. So secure boot is a very, very good way that we can see that we can protect our system. So those are some of the options that I want you to be aware of. Remember that sometimes you will also have additional things too, which we don't see in here, is things like chassis intrusion protection, Ronnie. I know I've seen that on some of the Dell systems and some like the Optiplex systems, and even some of like the Lenovo, their equivalent like the Think Centers, where they actually have an IDS, an intrusion detection system. Now, please understand that what we're talking about is a chassis intrusion detection system that allows us to know somebody's opened this machine. And if you use that in combination with things like secure boot, then it ensures that you have a trusted operating system bootstrapping the hardware, and also you can be aware that somebody's opened the case. So keep in mind some of the settings that you can use with your BIOS, with your UEFI. Understand some of the differences, and remember, at the end of the day, the firmware platform is what allows us in the early stages of the boot process to detect that all the hardware is available, it's operational, and then we turn around and we look for an operating system to finish that boot process. MBR is used in your BIOS, GPT is used inside of UEFI. If you can identify some of these settings, then in a certification endeavor where you're sitting into a scenario, you should be able to make the right choice. But you might, and might commonly actually have to support somebody in a support desk role where they don't know what these settings are, and you need to be able to identify them so that you can help them at the end of the day make the right decision.
Thank you for watching IT Pro TV.